tell us something about long-term analysis of peatland subsidence in 2 intensive agricultural used lowlands in northern Germany. Okay.
Oh, yes. Okay. Thank you very much for inviting me or us to this conference. It was postponed a lot of time, and in the end of our project, we are aware about this possibility to also present something of our findings in our project. And as we mentioned, or as we heard in the session before, we have some nice infrastructure that give us an idea what is land subsidence is. You see here, now I try this laser sword. Yes, you see here this. It's a pipe. It's a groundwater pipe with exactly the knowledge where and when it is installed. It was in the 1989. This was a former surface, and afterwards, now we come back to this site and we find that the pipe is growing. So, but it's not growing, but the land, the surrounded area is subsided. So just to have it in mind. So, but first of all, I will give you a short overview about our project network. We are in a multi-stakeholder approach. We work in 2 different regions, and we are more or less not so much focused on land subsidence, but also focused on them. We have 3 different partial project. So I represent here the soil science cluster from represent Humboldt University and also the Christian Albrecht University of Kiel. But we have also colleagues from the Thünen Institute who do some socioeconomics assessment of based on company level, and then we have also a small company EFTAS who do the remote sensing part in our project. And our main goal is to quantify and assess the peatland subsidence rates in the different regions. And another focus also for land subsidence was to use the land subsidence or the vertical movement from the Sentinel satellites to assess the soil moisture and also the moisture content in the whole area. So that was the focus on the remote sensing. So it's not only to quantify the land subsidence, but they want to use these movements to quantify the soil moisture in the area. As we all know, maybe, and I also learned today that peatland are soft soils, and often in summer times we go outside and have to learn that it could be also hard soils. We can drive with our car on the peat soils without any effect, hopefully. So, but now we all see that drainage of organic soils or peatland soils lead to an increasing drainage here. Yeah, you will find exactly a mire loss, and then also increasing degradation. So you can ignore this whole abbreviation here. It's only some German special thing about soil science. But what is the main challenge about this? We are all working on farmland, on grassland that it's already used, and this progress is already ongoing. Yeah, so. If you want to use the grassland, you have to drain it. And after a couple of years or maybe decades, you have to drain again because the groundwater level, the former groundwater level, comes closer to the surface, and you have to drain again. And if we also look for raising sea level, we have the problem exactly for one of our study sites in the northwestern part of Germany. There, an average of the high level is close to 0, so close to the sea level. It makes no sense to maintain the current land use, and this was one of our questions in the project. Yes, so let's have a look on the study site. We are here in Germany. This is This is a part of Germany, maybe you know this. And one of the study sites are situated 100 kilometer northern from Hamburg. It's Eidertrine Sorge lowland. It's in Schleswig-Holstein. And the other one is situated 70 kilometers northwestern of Berlin. It was in the eastern part of Germany. Both are formed by paludification processes. Is it okay or is it for me? What is it?
We don't know.
Okay, let's see if it comes back. Okay, and you can also see that we have different different areas of the different regions, and both are dominated by lots of intensive grassland companies or farms. If you say the most important difference are that in the ETS, I would say now, is that we have a lot of small intensive grassland for feed production, and in the UP in Brandenburg we have some large farmers dominate the whole region, and but both of them are very intensive used. And for the ETS, we have a mosaic of different soils. We have box, we have fen soils, we have also some peaty soils in the surrounding area. We have mineral cover very close to the geest edges. And in the UP, we have more or less dominated by shallow fen soils, underlaid by sand or some other calcareous sediments. So this is a situation we have already, and now we have a lot of talks about remote sensing and so nice pictures how we can go in the field. But my focus is more or less to go back to the ground, back to the history. And in both of these regions, we have a lot of old history data, archives full of very specific and very detailed information about the soils. And it's 100 by 100 meter. We have a historical soil profile, completely with coordinates and also the depth and also the substrate. And we want to look what kind of potential we have to use these old archive data for land subsidence in this area, in these regions. Just to have it here, so it's just for your information. So it was in total 24,000 historical soil data that we can use in the ETS, and also 10,000 historical soil profiles for the Upper Rheinluch. And we also use the digital surface models and orthophotos that we can focus what's happened in the field. So because our approach was to look at exactly the same position of the historical soil profiles and look what has happened until now. So the profiles recording dates was normally in the 70s. During its so-called melioration, it was improvement of land. Now nobody will say this in this way, but in the former times they need land for the farmers, and they have a very, very good information about the whole amount of peatland there. Yeah, and what are the main focus was to select sites. We are looking only, or we are limited because of our small staff only on grassland side. As you saw before in the slide before, the most dominant land use in the different regions was grassland, so it makes no sense to focus also on agriculture arable land. So we are focused on grassland sites that is completely grassland. So from the 70s to now, it was also not so easy to find out sites that are completely under the same land use for the whole time. And we have also find out that some of the fields we are going, and they say, oh, here's every time it's grassland. It wasn't any time grassland. So yeah, And then we have also looked for complete historical soil profiles, because the authorities often give us historical soil profiles, but ends until 2 meters. And afterwards, there was no information about the bedrock. So we cancel that point and look only for the complete historical soil profile. Yeah, I say the continuous same landscape, and clear it must be representative for the region, so that we have not only shallow fans, but we have also other structures inside our data sets. And it's also clear we have here, you see it on the map, these are the on this side, I hope. Yes. I think I have not so good view like you on this screen. So I have to imagine that there are some yellow points, but you can see it here. Very good, yes. So there are yellow points. That was our reference points, and as you see on the other map here, the big red color is only some small points. We have these 10,000 soil profiles here, and the greenish one here. Yeah. The green are our reference drawings. So we have a lot of groundwork to see what's happened exactly with our soil profiles. Yeah, and then we think about how we can use these soil information to calculate, to estimate, I would say, the land subsidence, the peatland land subsidence for our findings. And we use this kind of a model approach. It's a very easy differential equation that consists from 2 parts, I would say. The first part is more or less this in brackets, yeah, where we they are described the sorry, that describe the different subsidence processes in the aerated zone, I would say. And we use these profile information for an input for this model, like the profile structure. So did we have a mineral cover? Did we have very compacted topsoil? And also we use the current groundwater level. And all this together gives us also here together this coefficient for the mineralization and subsidence in different depth intervals. So we take 2 different depth interval, because we see that we have in a very top layer we have different processes. We have normally it's completely drained in the first 40 centimeters, and then we have a lower, I would not say topsoil, but this is more or less in the zone of dynamic groundwater movement. So, and we have differentiate between these 2 zones, and then we have also these kind of an constant loss here. That it's due to isostasy or also compactation of the deeper organic layer due to the compacted layer in the topsoil. Yeah, so we have to differentiate between the different zone on the profile. Yes, so and here we have some results of our investigations of different soil profiles. Here you can see, I have to, hopefully you can understand me because I cannot see anything on this screen. We have differentiate between thickness classes. Thickness classes means the former thickness class of the peat, of the organic layer. We differentiate in different classes, and then we have a look how much organic layer we have in the soil profiles. And we see here this is a subsidence per year, and we see at least that in the thickness class that are lower than 30 centimeter, have a lower subsidence rate than in the higher classes. And you can also see the differentiate between the different regions. And the reason why we have here in the more than 200 centimeter no profile in the upper Rheinluch, it depends on we haven't got any peatland soils that is broader than or depth deeper than 200 centimeters. That's why we haven't got any historical data here. So the mean subsidence rate we calculated is 0.7 centimeter per year. And then we have also taken to account if we have a kind of a mineral cover, because it's very common in both regions, mainly from sandy soil, or we have a kind of we also call it clay soil. I think it's also common here. That is clay or silty in the very upper layer. If we find this kind of mineral cover on the peatland soil, we also calculate the same one. What is happening with the land subsidence if we look at different mineral topsoil substrate? If we have no substrate, it's not a very clear conclusion, so we cannot say it's there is no difference, but we cannot also not say there is a difference. So for now, we cannot only say there should be. It depends on the substrate if we have, and it was very interesting to see if we have clay or silty substrate on top of the peatland soil, then we have slightly a higher subsidence rate. But if we have already sand, so then we have not such a high difference between the different soil profiles. Okay. Yes, so my time is coming. So there how many? Okay. Yeah. So just to put it in the area, so where we are talking about, because the local authorities and soil and water associations are very interested to see what's happened in their region. Because they want to ensure the infrastructure that's for the maintenance of current land use. It's good to see and good to know where exactly will be happen what. And what we can see here, for example, the ETS, we have here 5 classes. It's very easy to see that the whole peatland area is a subsided area. So we will not have some areas where we will have a kind of an up leveling of the soil. We have only a subsidence in the organic layers. And there's another slide for the other region. We also see it here. We will find some higher zones where we have higher subsidence rate in the very shallow channel here. But this is also a channel that it's characterized by very deep peat, and it's very intensive used. And we will also think about how we can do here an adapted land use, so that we haven't got any so hard consequence of doing the same rates here. And then one point, because I also learned today that soccer and hockey cannot be comparable. So, and I have copied in just before my presentation comes up here, uploaded. I heard you then. We want also to compare it with radar information, and our colleagues from the remote sensing team have also do a vertical movement based on the radar interferometry approach, and they come to this result. So it's, maybe you can see this. This is this area. We zoom in this area here, where we have this yellowish one. It's a bit smaller subsidence rate, and the orange or dark orange part is a bit more higher subsidence rate. And if we go to this side, we have, and interestingly here, also very high subsidence rate based on a different approach. We cannot compare it what I know now, but it's good to know that there's not so much difference between the different approaches. So thank you very much.
Right.
I would say, yeah.